Okay, so let's talk about the concept of total work. So far we've talked about the work done by individual forces, right? We talked about the dog pulling the skateboarder, and the force of the dog on the skateboarder was doing work, right? That force was doing work on the skateboarder. But maybe there were other forces also doing work on the skateboarder. For example, maybe the force of friction was doing work on the skateboarder. So for each force acting on an object, we could calculate the work done by that force, right? Each of those work that we calculate from each of those forces is going to be just some number, right? Work is a scalar. So we could calculate the total work done on an object by just adding together the work done by each force on that object. So that's our definition of total work. And so there's really two ways to do this. We can add together the work done by each individual force acting on the object. Sorry about our spelling issue here. Okay. We can add together the work done by each individual force acting on the object. Um, as I just said, you could add together the work done by the dog on the skateboarder and to the work done by friction on the skateboarder, to the work done by gravity on the skateboarder, to the work done by the normal force on the skateboarder. Add together all those works, and we get our total work. The other way to calculate total work is to first calculate the net force acting on the object, right, some vector that you get by adding together all the force vectors acting on the object. Once you know the net force vector, you can use that to calculate the total work done just by calculating the work done by the net force. Right, so there's two ways to do this. Let's go through an example. Let's say we're pushing a box horizontally, as we were talking about earlier, and let's say so we have some displacement in x. We're moving this box 10 meters along the plus x direction. And there's a few forces involved here. We've got the force of a push, which is equal to 9 newtons. We've got the force of friction, which is equal to minus 2 newtons, right, opposing our motion. And then we know there's a force of gravity. We know it's a 3 Newton box. That's the force of gravity acting down. And the normal force, therefore, must be 3 newtons acting up. So let's calculate the work done by each of these individual forces. The work of our push, we can use our constant force work definition. It's just force times displacement in x plus force times displacement in y. But displacement in y is 0, or we're only moving in x. So this just becomes 9 newtons, the force of our push, times our displacement, 10 meters. And so we've done 90 joules of work. The force of the push does 90 joules of work on the box. What about friction? Friction is in the opposite direction, so it's a negative force. It's in the negative x direction. So the friction force of minus 2 newtons, multiply that by a displacement. Negative 2 times 10 is negative 20 joules. So friction is doing negative work. That force opposes our displacement direction. So that's negative work. What about gravity? Well, gravity is down, but our displacement is to the right. So that's perpendicular. That's 0 work. Or using our equation, our force is a 0x component. So that term is 0. We have 0 displacement in y, so this term is also 0, so the work done by gravity is 0. Likewise, for the normal force is perpendicular to the displacement direction, so that's also doing 0 work. So there's 4 forces acting on this box, and we can calculate the work done by each. And each of it is just a number. So if I want to calculate the total work done by each of those forces, I just need to add together. For the total work, take the work of my push plus the work of friction plus the normal force work plus the work done by gravity. So that's 90 joules minus 20 joules plus 0 plus 0. And so the total work done on the box is 70 joules. Okay, so that's not so bad. The other way we could have done this is to first calculate the net force. So obviously the forces in y are canceling, so there's no net force in the y direction. In the x direction, we have two forces. We have the force of the push, and we have the force of friction. So we've got F push plus force of friction, and I can just adding together all our forces. So I've got a 9 Newton force in the plus x direction. I've got a negative force in the minus x direction, right, due to friction. And so the net force in the x direction is 7 newtons. And so the total work done in x, the total work done in general is just our net force in x times the displacement in x plus the net force done in y times the displacement in y. So to calculate the total work this time, we're just going to use our work formula, but instead of plugging in one individual force here, we're going to plug in the components of our net force vector. And so our net force in x is 7 newtons times 10 meters our displacement, and that gives us 70 joules. So we get the same answer. Okay, so there's two ways to calculate total work.